Hi, today I'm going to show you how you can use the laser scanner in a newer iOS device to create useful 3D models for earthquake response, paleoseismology, and other geoscience applications. Disclaimer that I'm in no way supported by Apple. Unfortunately, being in the UK, there aren't any nearby active faults to create a demo for you, but fortunately, I live down the street from an Egyptian tomb. Here, I'm using the 3D Scanner app. It's important to move slowly when you're scanning to avoid motion blur and make sure that the geometry is correctly scanned. Please check out my website below if you'd like to explore this and some other models yourself. I recommend using the free software programs Sketchfab, Cloud Compare, or Blender as ways to view, share, edit, and annotate your models. This video is sped up 4 times. This total scanning and processing time was exactly 4 minutes. The result is a photo-textured 3D model with real-world units. Let's compare this to a photogrammetry workflow. To produce a scaled SFM model, a control survey must first be established, then photos taken, uploaded to a semi-powerful computer with expensive photogrammetry software, and processed before the model can be viewed. The fastest I've ever been able to produce an SFM model was about 30 minutes. In my experience, it frequently takes multiple iterations of both methods to produce a quality model. iOS LiDAR has a clear advantage in time, effort, and accessibility. As I'll show you today, the final image resolution is acceptable, but a bit less than that from a high-quality SFM survey. Now for a real-world example. During an initial project kickoff visit to Azerbaijan this fall, we were only allotted 2 days of field time to do some rapid reconnaissance. Here, the Iranian plate is crushing into the Caucasus Mountains at a rate of about 8 to 12 millimeters per year, and we think most of that is accommodated by this massive thrust fault. We aren't aware of any prior paleoseismic work. At the site, I'm going to show you a fault intersects a natural river cut. Due to the time constraints, we only had about 45 minutes to spend at this site, similar to many earthquake response situations. When we arrived, this crew was in the process of destroying this natural fault exposure to build a new irrigation canal, so scanning the site quickly was our only option. Here's a preview of the model. This model is also available on my website. The outcrop is convex, and due to the height, scanning was difficult. Using Blender, I can create a 3D trench log. I can also make measurements in the model. I can then export the model. Here's the exported ortho image. On the right, subhorizontal cobble and silt layers rest on top of the dipping and apparently folded cobble layers to the left. At the lower right of the image, the cobble layers appear to steeply warp down. I interpret that this folding is a result of coseismic deformation, but that the main fault is still buried. The horizontal layers postdate the earthquake. This is a completely usable quality for a publication figure. Here's a zoom to show the image detail. The scan is rather low resolution due to the scale of the outcrop, but small gravels are visible. An SFM model could be quite a bit higher resolution, but we did not have a computer or survey equipment with us on this trip. Thank you and good luck.